Okay, so let's look at this problem. It states that a car with an initial velocity of 60 miles per hour needs 144 feet to come to a complete stop. Determine the stopping distance of this same car with an initial velocity of A, 30 miles per hour, B, 20 miles per hour, and C, 10 miles per hour. Note the rate of change of velocity is not affected by initial velocity in this problem. Fast cars and slow cars slow down at the same rate. So now let's look at what information we're given. We're given initial velocity, which is 60 miles per hour. Initial velocity can also be written as VO. Okay. And then there we go. This is how far it's going until it comes to a complete stop. It's 144 feet. That's also known as our displacement, which can be written as delta x. And then lastly, we know that once it comes to that place, it comes to a complete stop. So this can also be known as our final velocity, or VF. And VF is going to be equal to 0, right? It's traveling at 0 miles per hour if it's stopped. Okay. And then it says determine the stopping distance of this same car. So it's saying if we change our initial velocity, how does that change our stopping distance? How does a change in VO change delta x? And then also we're given the note that the rate of change of velocity is never affected. So the rate of change of velocity can also be called acceleration, or deceleration in this case. So it says fast cars and slow cars slow down at the same rate, which basically means whether the car is going 60 miles per hour or 30 or 20 or 10, acceleration will always remain the same, though we don't have acceleration yet. So now let's look at how these fit in with our kinematic equations. And our kinematic equations show how everything is related, right? So if I look at the information that's given, my initial velocity, my delta x or displacement, and my final velocity, I can see that it best fits equation 4. That's perfect because we only have one piece of information missing here, and that's A. And so we can rearrange this equation to solve for A based on the information we have. So again, our equation is, let me see if I can write it out, if this will work. Kind of. V squared is equal to, V squared can also be known as VF squared. That's our final velocity squared, is equal to our initial velocity squared. There we go. Plus 2 times acceleration times our displacement. Okay. Next, I'm going to move everything over to the other side so that we get A by itself, since that's what we're solving for. So we've got our final velocity squared that's already here. I'm going to subtract initial velocity from both sides, so that ends up on one side. And then I'm going to divide by 2 and divide by delta x. And then we're left with just acceleration by itself. So this is our equation for finding acceleration. Okay, and then another thing to note before we plug our numbers in is that so far we've got both miles and feet measuring distance. So we need to convert our units so they're using the same unit of measurement. So in physics, we use meters, and then we're also going to use seconds. And we'll just use the conversions that have already been given to us. And so for our velocity of 60 miles per hour, 60 miles per hour based on our conversion, we'll get 26.8 meters per second. And then for feet, we have 144 feet, and that can turn into 43.9 meters. Since we're plugging them into the equation, we need to make sure everything's in the same unit of measurement. We're going to use meters and seconds. Okay, so knowing that, let's start plugging our numbers in. So final velocity we know is 0, so that's easy. 0 squared is 0, minus our initial velocity, which 60 miles per hour converted into meters per second. That's going to give us 26.8 meters per second. And that's all going to be squared. I'm not sure why some of the lines are showing up and some of them are not. Oh. And then can't forget the 2. And then our delta x, which written in meters is going to be 43.9 meters. And then ultimately that should give us A. And then if we plug everything in, solve, use a calculator, we should get acceleration is equal to 8.2 meters. And as always, we measure acceleration in meters per second squared. If we cancel out our units in the original equation, we should be left with meters per second squared. Okay. And also, now we know our acceleration. That's going to apply to all the equations for A, B, and C, since the rate of change of velocity is not affected by initial velocity. Okay, so that's the first part. Now we can go into solving for A, B, and C. So we'll use the same equation actually. So same equation, v squared is equal to, final velocity again is equal to initial velocity squared plus 2 times acceleration, delta x. Okay. And then that should give us, so now we're solving for delta x because we're determining the stopping distance, right? We're looking for our displacement. So now we're going to change it to, we're going to rearrange it, final velocity squared minus initial velocity squared over 2a should give us our delta x, should give us the stopping distance. Okay. Let's see. I just do that. Just some technical issues. Okay, that should work. Okay, so let's just solve for A and know that the same process is going to work for B and C. So we're plugging in our final velocity squared Well, that's just 0. Okay, minus our initial velocity. In this case, now it's 30 miles per hour. 30 miles per hour converted into meters per second is 13.4. That's a 3 squared. Okay, and that's going to be all over 2 times acceleration, which we solved for earlier. And that's 8.2 meters per second squared. Okay, and then if we solve for everything, we should get, so everything's plugged in correctly. We're looking for delta x. Delta x is going to end up being 10.9 meters. And then if you convert it back into feet, since that's how it was in the original situation, then we should get 35.7 feet. And that's the answer to A. So when the car is traveling at an initial velocity of 30 miles per hour, and then we brake, it's going to take 35.7 feet in order for us to get to a complete stop.